Okay. Did you guys get a couple things written down? Quickly, let's go. So here's what the assignment was for the camera. Write down 2 things you thought were interesting from the chapters that we read. Who wants to say one thing? Tom.
Absolute zero can never be reached.
Absolute zero can never be reached. So there's actually some argument about that, believe it or not. There's scientists working on this all the time. Do you remember what the definition of absolute zero is? We're going to go in it in a little bit.
I can't remember the exact number. 200.
Right. Well, what does it mean from a physics perspective, though? All the molecules stop. There's no more kinetic energy in these molecules, right? Well, that's really impossible from a quantum mechanical point of view, which is basically a little more advanced than what we're going to go into here. But from the standpoint of the vibration itself, you really can't stop a molecule completely from vibrating. However, there are physicists like MIT or whatever who are trying to do this stuff all the time. And what they do is they end up banging molecules together at the exact same speed, and one of them they kind of stop, and anyway, they can get temperatures down really, 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 really low. But you're right, technically, or really, it's virtually impossible to do that. Whether it's actually impossible is probably still to be determined. Okay, somebody else. Yeah, Bobby.
One cool thing I remember was the bottom of a pond remains at 4 degrees Celsius even when the top freezes.
Yeah, we're going to get into that too. The bottom of a pond remains at 4 degrees Celsius even though the top can get much lower when it's freezing out. The good news about that is fish don't die, right? We're going to do that too.
Ice hockey on it.
Yeah, well, that is exact. Well, you could play ice hockey on a completely frozen lake, right? But all the fish inside would be dead. So that's good. All right, somebody else? Yeah.
I was talking about the molecules, how it heats up, it jiggles faster.
Uh-huh. There you go. When the molecules heat up, they jiggle faster. That's kind of the point of heating something, of providing it more energy. They vibrate faster. Good. About somebody from the front, Brian?
Heat goes from, if there's cold to never cold to hot unless an outside source influences it.
Oh, yeah. Energy always goes from a hotter source to a colder source, right? That is pretty cool. Yeah, that is pretty cool. That's kind of neat. Yeah, Nicholas.
I read about the laws of thermodynamics.
Good.
The heat never spontaneously flows from the cold substance.
There you go. That's what Brank was just saying. Heat never flows from the cold to the hot. Yeah, that's kind of cool, isn't it? Now, supposedly there's 3 laws of thermodynamics: first, second, and third. Did you read the little footnote about the 0th law of thermodynamics? It's actually a 0th law too, which we can mention when we get there. But all you need to know are the other 3. Okay. Anybody else have a good one they wanted to do?
I didn't know there was a difference.
Hang on, Brank. Go ahead, Andy. No, go ahead, Andy.
Oh, I didn't know there was a difference between capital calories and.
There you go. There's a difference between capital big C calories and little c calories. Sure, yeah. You don't think about that. Normally they report the ones on the side of your food in big C calories, I think. But what's the equivalent in metric terms?
Kilocalories.
Nope. You had it right here. Joules, because it's just energy, right? It's just energy, even though heat is just a flow of energy, which we'll get to. Good. All right. You had one more.
Cold was just the absence of heat, essentially. It was the absence of thermal energy.
Cold is when something's colder, it's got less thermal energy in it. Very good. Or internal energy. Good. Very good. Okay. Yeah, Nicholas.
Thermal expansion.
Thermal expansion, yep.
Different substances expand at different rates.
Absolutely.
Iron, brass.
Different substances expand at different rates? Yep, I'll show you a little video on that. Yeah, I'll show you a video on that. If you have an old school thermostat on your wall at wherever you live, then I guess the clues all have air conditioners which have thermostats, but they actually use the fact that there's 2 different types of material that are glued together or welded together to change depending on how warm or cold it is.
Why the aluminum is more resistant to heat than copper?
Why aluminum is more resistant to heat than copper? They talk a little bit about that. I think they mention iron in the book, but yeah, the molecules are actually much bigger in iron than in silver. So the same number of molecules can actually heat up a lot faster. That's part of it. Anyway, good. All right. So here's what I want you to do. Put your name on it. Is it on? If it's on somebody's notes, actually, don't worry. Did everybody get a couple things? I'm going to take your word for it. Did you get a couple things? OK, good. All right, then. Don't worry about it. Good job. That was a pretty good thing. Now we kind of got our blood flowing for this today, too, right? Which is, oh, great. Please don't restart. Extend 4 hours. OK. I wanted to show you something I totally forgot to show you when we talked about energy. And it's one of my favorite videos. Hopefully I can find it here. It's all about the transfer of energy and how energy is neither created nor destroyed, kind of. Anybody ever heard of a Rube Goldberg machine?
Yes.
Well, a Rube Goldberg machine, you want to describe what it is, Tom?
It's a way to make a simple act very, very complicated.
It's a way to make a simple act very, very complicated.
There's actually an AFN commercial on how to turn a light switch off.
There's an AFN commercial on how to turn a light switch off using a...
Yes.
That's pretty cool. That's pretty cool. OK, let me see here. OK, so this is one that was done by, I'm about to show you a video. It was done by Honda. It's actually a takeoff on a 30-minute long video. 30-minute long video. This one's only 2 minutes. Sorry, you don't get 30 minutes of video. But trust me, I've showed the 30-minute one to classes before, and by the end they're like, no, please make it stop. Although it's very interesting. They're like, I can't believe you made me watch that. There's no talking in it, and it's just panning, like a video panning across the screen. You'll see, it's very similar to this. Nicholas, you want to hit the lights? And then we'll get this. Then I said this was made by Honda a few years ago, and I think you'll like it. OK, I'll turn the other lights off too. Oh, hold on. You know what? You're not getting the sound. Hold on a sec. And you're getting an ad.
Scientology.
I know, Scientology, of course. Where'd it go? There it is. Let's see. Yeah, anyone know where the power is, or the sound is? There. I got it. There we go. That'll do it. OK, let's try this one more time. And these are all the parts of a Honda.
Engineers were bored.
Isn't it nice when things just work?
Now, I promise you I wasn't paid by Honda to show you that. But isn't that cool? It was kind of a cool way of demonstrating the energy thing. And it took, supposedly it took many, many hundreds of takes. There was no computer graphics in that, by the way. It's all real. And it took lots and lots and lots of takes. And I think they had to splice it in one location. Like they couldn't get it exactly right the whole time, so they had to splice it once. But other than that, pretty good. Pretty good. You want to hit the lights, Nicholas? Did you have a question, Bobby? Yep. All right. So that was back on energy. Now,
Dominoes are kind of like that, right?
dominoes are like that. Yeah, the energy in a domino, when it's standing up, is what kind of energy? Potential energy, right? Because you tap it and then it falls down, and that's when it causes sound and motion and all that. Yeah. So good. All right. So we all know that we read this week about thermal energy and heat transfer. So we're going to go through this, and hopefully, since we all read this, we'll kind of be able to breeze right through it. I have some other little videos I want to show you, a couple of demos that I think are kind of interesting too. As with last week's topic on energy and some of the other things we've talked about before, thermal energy and heat transfer, thermodynamics is what it's sometimes called, is a huge, huge topic. I mean, you can spend entire semesters just talking about this, and entire careers, if you want, just talking about this. So again, it's one of those things where this stuff is, we're going to kind of touch the surface of it with a lot of this stuff, but hopefully you'll get a good feel for it when we're done. Okay. So thermal energy, we all kind of know what it means when we say thermal. We have thermal underwear, makes things, makes us stay warm in the winter. But thermal energy has some kind of terms we need to talk about. Number one is this thing called temperature, which you guys all know kind of intuitively what temperature is, right? And temperature is not heat. And later when I ask you what heat is, don't use the word temperature, right? But temperature is not heat, okay? Temperature is either how hot or how cold or somewhere in the middle. I've totally forgot to bring a couple of cups for this. We'll try this during the lab tomorrow. But if you take a cup of cold water and a cup of hot water and a cup of warm water, and you stick your one finger in the hot, one finger in the cold, and then you stick both your fingers in the warm, it feels totally different. Like the warm does not feel the same to both fingers. And we'll try it, and you'll go, oh yeah, I guess that's true, right? And we'll, as you guys already learned in some of the reading, we'll find out why that's the case a little bit later. But the idea is, of course, this finger's going to end up with more energy, and this finger's going to end up with less energy, and this one's going to have, we're going to have heat going one direction or the other when we get to that point. Okay? Anyway, we measure temperature, obviously, with a thermometer, and there's no real upper limit. We already mentioned the fact that there's a lower limit to temperature, but there's really no upper limit. What would happen if you kept increasing the temperature? Well, there's kind of questions about what might happen. Because it's all about an individual molecule's speed when we get down to what temperature actually measures, and kinetic energy. Can you get so fast that the molecules all breaks down? Maybe. I don't know. But anyway, there's no real upper limit for all practical purposes. Okay? Temperature itself, it's all about how fast in a gas, how fast the gas particles are moving or bouncing back and forth. Remember, in a gas, the particles are individual. The molecules are all individually kind of floating around in whatever container you have it in. In this room, it happens to be the air. And the temperature is just how fast the gas particles are bumping into each other, bouncing back and forth. For a liquid, well, things aren't really bumping as much, but they're kind of sliding past each other and jiggling. They do bump around to a certain extent, but it's still the sliding and jiggling and how much kinetic energy and how fast those particles are moving. And then in a solid, nothing really moves from one place to the other. The molecules themselves stay in a fixed location in a solid. Okay? So it's basically how fast those particles are jiggling back and forth. Okay? When we talk a little bit more about the chemistry part of it, you'll see that molecules actually do a lot of jiggling and a lot of vibrating in lots of different directions. And that speed and that kinetic energy is what we call the temperature. Okay? We're going to measure temperature in here in either Celsius, which you've probably all heard of, and then Kelvin, which until you read the chapter you may not have heard of it. But Celsius is kind of like our Fahrenheit scale in that it measures the kind of the lower numbers are numbers that we deal with every day. What's 0 degrees Celsius? Freezing of what? Water, right? Very important. Fresh water, actually. Okay, freezing of fresh water is 0 degrees Celsius. 100 degrees Celsius is when water boils. Okay, and then everything in between is the kind of the normal temperatures. Was anybody here last July? No, you guys, nobody was here last July. The maximum temperature here is around 40 to 45 degrees in Celsius, which is about 110 to 120 degrees. In the easy way, by the way, they give a little formula in the footnote in the book. The easy way to make a real quick calculation is to take the Celsius temperature, double it, and add 30. So if I said it was 40 degrees out Celsius, yeah, 80 plus 30, about 110. So yeah, not too bad.
It was 120 last year.
Well, yeah, it gets up to 100. I looked, the absolute maximum, supposedly in Djibouti City, has only been 117 maximum. That's what they say on the interweb. But, and I actually asked the HOA weather people. Well, you have to add the actual what it feels like is like 130 or something, 135 or something crazy like that. So, anyway, that's what temperature is. Okay, and we're going to use Celsius. Now, Kelvin is the one that we use generally in science class when we're talking about absolute temperatures, because 0 Kelvin is what temperature?
Absolute zero.
Absolute zero. Okay, 0 Kelvin is absolute zero, and that means it's easier to figure out what's going on. If something goes from 100 Kelvin, and by the way, we generally don't use the little degree symbol for Kelvin. They changed that in 1968. Not sure why. They just decided all the other units don't have it, so why have this one have it? But if you go from 100 Kelvin to 200 Kelvin, you've actually got twice as much temperature, okay, because it's an absolute scale. If you go from 100 Celsius to 200 Celsius, not quite the same. Okay? Why? Because you didn't start Celsius at 0, absolute 0. So it doesn't twice, if you double a Celsius temperature, it's not twice as much temperature. Even though the number is twice as much, it's not twice as much because it goes into the negatives. So we could graph it out and kind of show you that, but it's not. Just keep in mind that the Kelvin scale is used because it starts from 0, and that's what makes most sense when we're doing calculations. So if I made you do any calculations, which I may or may not, but I doubt I'll make you do any temperature calculations, you should generally use Kelvin, especially if you're dividing or multiplying. It doesn't quite work if you don't. Okay? Yeah, Tom.
Now, what is centigrade?
Centigrade is also Celsius. They're equivalent in this case. Yeah, I forget why we use Celsius versus centigrade, but they're the same temperature scale. Yeah. All right. So here's absolute 0. I love this little chart in the book. It shows, I had to break it into 2 to fit on here. Absolute 0, the lowest temperature. We already talked about that. This kind of looks weird. It's at negative 273 degrees Celsius, or 0 Kelvin. Atoms or molecules have lost all available kinetic energy, and you can't get any colder. Okay? Well, some of the temperature scales on here are kind of interesting. Hydrogen bomb, 100 million Kelvin. Right? That's a lot of million. The center of the sun, which interestingly is also a hydrogen bomb in the sense that it's a nuclear fusion reaction. So I don't quite get why it's less, but I think maybe it has to do with other particles, lots of other particles or something. 20 million. Let's see. The surface of a hot star is about 50,000. So the surface, it gets much cooler. In fact, our sun, I think, is about 6,000 Celsius. Our sun is not a very hot star, as it turns out. Okay. Oh, here we go. That's right there, 6,000 Kelvin. Plasma. So when we get into the types of substances, you've got solids, liquids, gases, and then this weird one called plasma, which is basically when the atoms themselves have broken apart and they're not even atoms anymore, just particles like protons, electrons, neutrons, and that sort of thing. So it's kind of a mishmash. But that only happens at really, really high temperatures. Okay, you're not going to see that generally on Earth. Surface of the sun, let's see. Carbon light, arc light. Iron melts at 1800 Kelvin. Tin melts at 500. Water boils at 100 Celsius, which is about 273 Kelvin. No, sorry, 373 Kelvin. 273 Kelvin is 0 Celsius. It's an easy way to remember. If you remember 273 and say, OK, that's equal to 0, there you go. Dry ice. If you guys use dry ice to package like maybe foods or you can carbonate water with dry ice, actually. Dry ice actually vaporizes at negative 100 Celsius, which is pretty cold, really, which is why you don't want to really touch dry ice for too long if you can help it. And then you've got oxygen boiling. That makes sense when oxygen boils?
There's liquid oxygen.
There is liquid oxygen. In fact, normally when we talk about liquid nitrogen. I'll show you a little video on liquid nitrogen in a bit. Liquid nitrogen is mostly air, because air is mostly nitrogen. So liquid nitrogen is basically liquid air. Well, it's just like liquid oxygen is the gas oxygen that's been cooled down so much that it becomes a liquid. Kind of cool, literally cool. All right. And then you've got this helium boiling way, way, way down here at like 4 Kelvin or something like that. Liquid helium is very interesting. Turns out liquid helium, the particles in them have no friction, 0 friction. And like provably zero friction, which is kind of cool. Okay? So anyway, then you get down to absolute zero. Pretty cool. Do that. Okay? Anyone ever wonder how a thermometer actually works? Like you stick your thermometer in your mouth, right? And you're measuring the temperature of your body, or at least temperature of mouth anyway, right? How does it actually work? Well, there's a liquid in there generally. The new ones are all electronic, right? Or there's infrared ones, which actually just kind of take the infrared radiation coming off you. We'll get to that in a bit. And as the liquid gets warmer, it just expands. Right? If it's cooler, it contracts. And that's where you get the idea of how high up in the thermometer it is. Pretty cool stuff. Right? You read the thermometer. Remember how you have to wait like 90 seconds or whatever when it's in your mouth or until it beeps or whatever? That's because there's a thermal equilibrium there. That thermometer has to be the same temperature as the inside of your mouth, or at least the liquid inside does. Otherwise, it won't read correctly, because that's the way they calibrate the scale. Okay? Then we have these cool infrared thermometers, which means I could point it at the wall and tell you how hot the wall is. And I'm sure the special forces guys use stuff like that to like tell where bad guys are and all that. But no special forces guys in here, right? No, all right. Anyway, so that's how thermometers work. OK, so we talked about this a little bit earlier. Temperature versus thermal energy. Temperature of some object does not depend on how much stuff there is there. I mean, the more stuff there is, the harder it is to change the temperature of something. But the temperature itself doesn't actually depend on how much stuff there is. Okay? You can have 1 cup of water it's at 95 degrees Celsius, I forgot the degrees, 95 degrees Celsius, and has 8,000 joules of internal energy. Okay? And then if you pour half out, has the temperature of the water changed that's left in the glass? No, it's still 95 degrees Celsius. Now there's only how much internal energy left in that half a glass? 4,000, because it's half the amount with the same temperature, so it's only half the total internal energy. Make sense? All right, this isn't rocket science, this stuff. Okay? So the temperature of the remaining water is still 95. Internal energy, remaining water is half in this case. Which reminds me of a joke. You know how they say the glass is either half full or half empty, and if it's half full, you're an optimist, half empty, you're a pessimist? As an engineer, we say there's just too much glass.
Yeah.
That's what it is, right? I don't know if that makes us a pessimist or an optimist, but it makes us an engineer, that's for sure. OK, we already did this. Already got over the answers here. Which has more internal energy, an iceberg or a glass of boiling water?
Iceberg.
Andy says an iceberg. Kenneth says glass of water. Well, certainly which one's at the higher temperature? Boiling water, right? How much is in a glass of boiling water? How much stuff is there?
8 ounces.
This much, 8 ounces or 16 ounces, right? Right? How much stuff is there in an iceberg? Like trillions or millions of kilograms or whatever, right? So if you look at, even though the temperature is very low, Andy's actually correct, the temperature is very low, but it's got a lot of internal energy. Okay? And by the way, one of the ways to think about this is, even though it's cold out, things can still have internal energy. Because when you're trying to heat something in the winter and you happen to, let's say you're not burning something. Let's say you have a heat pump, like an air conditioner turned backwards would actually, remember, you know how the air conditioner, you go outside, it's warm on the air coming out? If you flip it around, it becomes a heater. Right? It just becomes a heater. And what it's doing is it's taking energy from outside and actually pumping it into your house. It's actually pumping that energy into your house. And if it's cold outside, it'll still take more energy out of the cold air. It'll make it colder outside and pump that into your house. So there is energy in large things that are cold, and in fact a very large amount. But it just happens that the temperature is low because on average the particles aren't moving that fast. They're still moving in that sense. Okay, good. All right. How about the thermal energy of a sparkler? This is kind of a picture. You know the little sparklers, 4th of July. You turn them on or you light them. Hang on. A lot of thermal energy in the jet right now, anyway. So the sparkler, each individual little spark is like 2,000 degrees Celsius. That should be a degrees. 2,000 degrees Celsius. Yet we let little kids hold them all the time, right? 2,000 degrees. Well, okay, so you do tell your kid not to like poke it near his eye, right? Because that'll probably be, or put it in your mouth. But really, each individual spark may have a high temperature and a lot of energy for that tiny little thing. But the total energy is really small, because you can hold it, and sparks will fly on you, and you're not getting like burned to a crisp, right? It's just not that much energy compared to the amount of energy in your hand. Okay, and there's really not much transfer of energy because there's a tiny little amount of energy to begin with. So that's the thing. So when we think about thermal energy, we got to think about size and temperature all together. Okay, all right. Aha, here we go. What is heat? Hang on. Andy, is that what you were going to say? What were we saying, Mike?
Transfer.
Oh, sorry. Frank, did you say it? Or either one. OK, heat. Good. Well, we already read it. So heat is the transfer of thermal energy. It's the flow of thermal energy because of a temperature difference. Okay, that's the only way we know how to transfer thermal energy is this temperature difference. Okay, heat is not how hot something is. Heat is not how cold something is. Heat is not, heat is not in an object. We can't say there's so much heat in that object. We can just say put two objects next to each other. Heat flows between them, and that's what the energy transfer is. Makes sense? It's an energy transfer. Okay, and we've already kind of covered this in the beginning class. The natural direction of heat is from a higher temperature substance to a lower temperature substance. It doesn't go the other way without doing some sort of work on that object. The only way the air conditioner gets energy or gets cool air from inside to the inside here, which is cooler than outside, we hope, the only way that happens is if it does some sort of work on the gas itself or some other gas and so forth. And so that's the only way it happens. Otherwise, the heat would just go straight out the other direction until it's equalized.
The freon of the coils, it runs across, the air goes across the coils.
The air goes across the coils, right? But what's going on? What's going on is the coil, the substance inside the coils, the freon or whatever it is allowed to expand. And then when you run the cold water over it, that actually gathers some of the energy. So, sorry?
The cold air.
The cold air. When you run the cold air over it, yes. Thanks.
And,
Okay.
Somebody said something about like it's the absence of energy. That the absence of thermal energy is what makes it cold, because it goes from hot to cold, so the heat
Right.
is getting sucked out of the air. onto
Yes.
The coils.
Yeah. The heat is getting sucked out of the air, right, on the
That's why
coils.
we get ice on
Right.
the damn things.
Right. We do get ice on there. I hate that when that happens. Okay. So that's what's going on there. All right. So let's look at heat here. A liter of water. A liter is half liter. Is that a half liter bottle? These are, I guess. I think that's a half liter, something like that. Anyway, liter of water left in a pot. In the left pot, rather, 3 liters in the right pot. Both pots absorb the same amount of heat, the same quantity of heat. Okay. Well, the temperature increases 3 times as much for the smaller one than the larger one. Okay, and why is that the case? Because, yeah, go ahead.
There's less room for the thing for them to bounce around.
Yeah, that's a good way to put it. There's less volume here of stuff to bounce around, so the heat goes into each particle 3 times, like 3 times as much heat goes towards each particle in this one versus this one. Okay, so that's what it is. Oh, I like how they put the little thermometer on here too with it. Yep. If you somehow put the same amount of heat in it. Okay, transferred rather. Okay. All right. So the quantity of heat, remember heat is just a transfer of energy. We already said energy was measured in either joules or calories. Okay? And here's a little definition of calorie. 1 calorie, small c, is the amount of heat needed to raise 1 gram of water by 1 Celsius degree. Okay? I don't really think you'll need to memorize that, but it's an interesting one to think about. 1 calorie is the amount of heat to need to raise 1 gram of water by 1 Celsius degree. What's 1,000 calories? 1,000 calories is the amount of heat needed to raise the temperature of
1 kilogram.
what's 1 kilogram by 1 degree. Okay? So that's interesting. So for every kilogram in your body, and let's say you're 45 kilograms, if you want to raise the temperature 1 degree, okay, 1 Celsius degree, you need 45, let's see, what is that? Let's see, what did I say? 45 kilograms, you'd need 4,500 calories is what you'd need to raise the temperature that much. Does that make sense? It doesn't seem to make sense. I'll have to think about what that means exactly. But anyway, the point is, you need to raise, well, and your body's not all water, although it's mostly water. Okay, so you can do this. Now, joule to calorie conversion, 4.19 joules, 1 calorie, little c calorie. And so 4.19 joules of heat will change temperature of 1 gram of water by 1 Celsius degree. Okay, that's just how we measure it. It's in joules. Remember when we drop an object and it bangs into the ground and it warms up a little bit? Well, there was a heat transfer there. Okay, and that heat transfer is just measured in joules, which is why we can add it to our total energy, like they did with the skate park thing the other day. Okay. Oh, that reminds me. I don't want to forget. Tomorrow for lab, if you guys could bring computers again, that would be good. Did you guys all see my email about the anonymous feedback? A couple people put things on there. Thank you very much. One of the comments was about the labs and how it was tough to get that lab working correctly, and it took time to read it, and it was it seemed to slow things down a little bit. My comment is, while I want you guys to like get productive work done in class, I also do want you to be able to read and follow directions for a lab. So for what it's worth, but I will try in the future to make the labs a little bit either less hard to understand, although that was straight from your lab book. So I don't know, but or I'll try to. Well, maybe we'll go over how to do each lab together on the board before we go. So I'll try. I'll take that advice. Okay. All right. Next. So to sum up here, heat, energy in transit, the motion of energy between two objects. Okay, it's measured in joules. Calories are big C calories. 1 food calorie, we already talked about this, 1,000 little calories. Okay, 1 peanut contains 10 big calories. So you know. I think I looked it up the other day. A Lifesaver's like, what did I figure, 15 calories, something like that for a Lifesaver?
1 calorie.
A Tic Tac's supposedly 1 calorie. That's right. That's right. Okay. To a scientist, the peanut releases 10,000 calories when burned. Little c calories. In other words, the way you figure out how much calories is in some sort of food item, you burn it, and you measure how long it takes to burn, and that gets tells you how many calories it is. Kind of cool. Okay. Same thing here. 4,190 joules, 1,000 joules, 41,900 joules of energy when you actually burn a peanut. There you go. Okay. All right. So here's a check question. You heat a half cup of tea, and its temperature rises by 8 degrees Celsius. How much will the temperature rise if you add the same amount of heat to a full cup of tea? 0 degrees, 2 degrees, 4 degrees, or 8 degrees? Or maybe 16 degrees. Add the same amount of heat to a bigger amount of water. Think about it this way. Let's say I add enough heat to raise the temperature by 8 degrees to that cup of water. Then I go to the ocean and put the same amount of heat in the ocean with my stove. Is the ocean going to get raised up 8 degrees? No. The ocean's not going to notice, really. And that little area around it might, but not the whole ocean, right? So it's going to go how much more? Proportionally, right? It's going to be 4 degrees. Because you've got the same amount of heat, but twice as much volume. Just proportional. Okay? All right. All right. So let's see. I'm trying to think if there's any Hewitt videos on. Whoops. Let me just see if there's any Hewitt videos on heat. I don't think there were. Let's see. Mastering Physics, Chapter 6 we're on, right? Videos. There are some videos here. Let's see what they are. How a thermostat works. Nope. Liquid nitrogen. Let's see. Here, let's look at the low temperature liquid nitrogen one. let's see, we'll do this here. Put this one back in here. Okay.
Hey, let's talk about this expansion and this expansion under different temperatures and everything. There's something here that's kind of neat today. Ted, can you give me a hand? Talk about low temperatures. Ted's brought over here some liquid nitrogen. This liquid nitrogen is about 190 degrees below 0 Celsius. It's really, really cold. Almost 80 degrees above the absolute 0 temperature. Now, can we have a volunteer jam a hand in there for about 5 minutes? Okay. Nobody gonna do that, right? Okay. Let's show how the let's show how the volume of something will change. Here's an air-filled balloon, gang. Okay, what's going to happen to the volume when it gets cold? How many say, oh, it's going to expand? Stand up. And what happens to the volume, gang?
It not only shrinks, it becomes like
Look at that.
really tiny.
Now it's going to start to warm up the air temperature. What happens to the volume?
Expands.
What happens to the volume? We bring it above air temperature?
See, it's getting even bigger than it was at air temperature.
You can go closer, Ted. Yeah. Let's try the flour. This is a flour Ted found out in the ground. It's kind of nice and limp, right? Kind of limp, isn't it? Okay? But what happens if we slow those molecules down? Yeah, why did it fizzle like that? What's going on? Oh, dang, did you see such a thing?
All right, well, there's your low temperature liquid nitrogen, liquid air they call it. The flour broke lots of pieces. Okay, I want to hit the lights. Sorry? No?
Can you buy liquid nitrogen?
Liquid nitrogen is kind of hard to come by. It's kind of expensive to get. They use it for things like welding applications. They use it in physics labs, chemistry labs a lot. So that's where I mean, when I've gotten it for teaching before, it's because I had a contact at the lab to do it that way. Yeah. So you can't really just pick it up at the store. You can't go to Walmart and get it. You can generally pick up frozen carbon dioxide or dry ice pretty easily.
Baskin Robbins, you can get it there.
Oh, Baskin Robbins? I didn't know that. All right, never knew. Okay, so now we're going to go into this idea of thermodynamics. Thermo being heat, dynamics being the transfer of something, or the motion. Thermodynamics, motion of heat transfer, movement of heat. Okay. We've got 3 laws here. We'll go through them relatively quickly. It's kind of similar in the sense to the laws, Newton's laws. There's 3 of them. Well, there's actually 4. We'll get to the 4th one after the first 3. First law of thermodynamics. When heat flows to or from a system, the system gains or loses an amount of heat equal to the amount of heat transferred. That actually doesn't sound too odd, right? Just says when you move heat from one place to the other, the system gains that amount of heat. Okay? The amount that you changed. Well, the other system had to lose that amount of heat. And so what that really means, okay, and the bottom line of that is, this is really a restatement of the law of conservation of energy. It's saying that anytime you transfer heat, you're never going to lose any if you take the whole system into consideration. Okay? In other words, heat added is the increase in internal energy plus whatever work is done by the system. Okay, so in that case, if you do work on something, you will increase the. Is that really what it is? The heat? I thought it was the other way around. Increase in internal energy is the heat added plus the external work done, or I guess it's minus. Oh, sorry, plus the external work done by the system. That's what it is. In other words, let's see if I can use a good example. If you have a cylinder, like this, if you have a cylinder, let's see if I can draw this like this, and it's got a little piston in it, like this. Okay, and this is all air in here. Okay, and the piston can move up and down freely. Okay, if you had a little flame here, okay, if you had a little flame right there, a candle or something, and you started heating up this gas, okay, the gas might get warmer, but it would also want to expand, like the balloon did, right? And this piston would go up. Well, it takes some work to move a piston against gravity, right? So that amount of work would be part of the amount of heat added there, okay? Because the work done by this system actually has to do work on something. So that would actually, you could actually do this. If you did it right, you could actually heat it up just enough. I'm not sure you could. I'm not sure this is actually physically possible. But I guess theoretically you could heat it up, and it wouldn't actually increase at all in temperature, but it would push the little piston up. In fact, I'm sure you can't do that based on some other conservation issues, but you can. But you could think of it like that. You can either do work because you're adding heat, or you can actually increase the temperature in that case, okay? Or increase the internal energy. All right. So that's it.
I don't
Yeah.
know if this had the same concept as hydraulic, but using oil instead of.
Yeah, it's the yeah. So Nicholas is saying it's the same concept as the hydraulic pump. Yes, in fact, your internal combustion engine does exactly that. It's got pistons in it. When you explode gasoline in there, right, you're actually doing work on that piston, which is connected to your drivetrain, which makes your wheels turn, right? And that happens depending on how many pistons you have. If you have a 4-cylinder car, those cylinders are really pistons, and that's connected to your drivetrain. So yeah, it's the same sort of thing. You're doing the work there. Different way to get about it, but do the same idea. Yeah, good thought.
Now the way a diesel engine works is it superheats the air inside of the piston and then sprays the fuel in, and that's what ignites it. So
Actually,
it's more like that, isn't it?
Diesel engines are based on compressing the fuel because of when the fuel gets when the air mixture gets compressed, that's what causes it to actually explode. Pretty sure that's what it is. But I tell you, let's look it up after class, because I know there's something interesting about diesel engines, but it's still the idea of the explosion causes the piston to go up. Do that. Okay. So anyway, cannot create or destroy energy. That's new. That's the conservation of energy. Really the same as the first law of thermodynamics. Okay. All right. Sometimes they say the first law of thermodynamics is you can't win. In other words, you can't do better than like what you started with in terms of getting more energy out of a system by like adding heat to it. Okay. All right. The second law of thermodynamics, and this one we've been talking about since the beginning of class. Heat never spontaneously flows from a colder substance to a hotter substance. Okay? Heat flows in summer, hot air into the cooler interior of a dwelling. When we flipped off the air conditioner, the air in here would not continue to get colder because it's hotter outside. So the air in here is going to have a heat transfer into the building, and you're going to get more temperature increase here until the building is the same temperature outside. Okay? Except for other considerations like re-radiation and all that. Okay? In winter, heat flows from the warm inside of a house, unless you're in Djibouti, to the cold exterior of a house. Okay? The only way you can get heat to go from cold to hot is when you do work on the system, or you add energy from some other source where you can make it do that. So we had to figure this out. Okay? Before we figured out how to make air conditioning and things, there really was no way of transferring heat from anything hotter to colder. You know, refrigerators, right? Refrigerators, the old refrigerators, you had to put a block of ice in it. Every winter, people would go out to ponds that were frozen, cut out blocks of ice, put them in sawdust. And why does sawdust? Well, sawdust is insulation, which we'll get to in a minute. And then they bring them back and they put them in rich people's houses in their ice boxes, right? Still kind of expensive to do that. But before we knew how to pump heat using work, we didn't have any other way to do it except for that. Okay? I have a question for you while I'm thinking about it. let's say I had a refrigerator. Let's say this, instead of the projector, this projector was actually a refrigerator. Okay? And it was sitting in the room like this. And the air conditioners broke. Okay, the air conditioners just stopped working. And some bright bulb said, let's just open the door of the refrigerator, and that'll cool the rest of the room. What's wrong with that observation? Or is it right? I mean, I guess it could be right.
The heat would transfer into the refrigerator, warm it up.
But you've got it plugged into the wall, so you're continually cooling the air inside.
You got a lot more heat going in.
Well, what do you mean by...
Depends on the size of the room.
Say again?
I guess it would depend on the size of the room.
I'm not sure it would depend on the size of the room so much as it depends on what you have to do to actually get the air inside cooled. Because do you ever go next? Well, here's another idea. Why do we always put the air conditioners on the wall such that it blows hot air out and cool air in? Why not just put it in the middle of the room so it blows the cool air and just more cool air into the room than hot air out the back?
Doesn't like the hot air have to have an exit?
Yeah, absolutely. The hot air does have to have an exit. Why?
So that way we can circulate the cold air from inside.
It's even more than just having to circulate the air. It's the idea that because you have to do work to cool that air inside, well, let's say the refrigerator, because you have to do work, extra work to do that, that energy has to go somewhere. The extra energy you put into doing that has to go somewhere. And it actually goes out the fan that's in the back of the refrigerator. I don't know if you've ever noticed, the bottom of your refrigerator is really warm, and it pushes warm air out, right? And if you're trying to cool your room, don't use a refrigerator. You would have to put a refrigerator like on a wall so as it goes outside. The air conditioner, same thing. You can't put an air conditioner in the middle of the room because it takes, two things are going on. You're taking the hot air from the room, doing work on it and making it cooler, but the act of doing work actually causes more energy to be released into the room, so it's a losing battle. You'd never be able to cool the room. So if you open the refrigerator, you might be cool right around the refrigerator just because the air is circulating around the room. And you might be right around the refrigerator. But the overall room will increase in temperature. Yeah, unless you somehow pipe the hot air out the door. Right? So I always thought it'd be a good idea to have refrigerators, in the summer anyway, refrigerators near the wall are actually with the vent outside. Same thing, you'd get the benefit. Of course, in the winter, it's a good thing for you. Right? In the winter, it actually helps heat your house, the refrigerator. So that's going on. OK. Heat can only flow cold when we actually have a heat pump of some sort or do work on it. OK. And then finally, almost finally, the third law of thermodynamics. No system can reach absolute zero. So these aren't like any more ideas than what we've already been talking about, right? First law of thermodynamics says you're going to if heat transfers from one system to another, then the total heat, like the amount of heat, the amount of energy that the other object gets is equal to the amount of heat you transferred, minus any work or plus any work that it does. Second law, which kind of makes sense, the conservation of energy. Okay? The second law says what? We just did it. Heat never goes from cold to hot spontaneously. Good. And then the third one is no system can reach absolute zero. Full stop. So these aren't that hard. There is this zeroth law, which I know you've all been waiting for me to tell you. Zeroth, I actually gave away the punchline. It is called the zeroth law, not the fourth law, because it's kind of more fundamental, I guess. I guess it kind of goes into this other thing. If object A is in thermal equilibrium with object B, call object B this room. Object A is in thermal equilibrium, meaning they have the same temperature. Object C comes along, and it's in thermal equilibrium with the room. What does that tell you about A and B? A and B. They're equal, actually. Yeah, they actually are also in thermal equilibrium. That's what the zero says. We don't worry too much about it, but in this class anyway. OK, so those are three laws. Tell you what, why don't we go on our break right now? I haven't heard the little thing yet, have you? Have you guys heard the little one yet? OK, let's go on our break right now. And then when we get back, we'll do the check question on this stuff. Okay? We're good? OK, thanks. For what?
There were times we're not allowed to use these down range now, right?
Really? Not allowed to use these? Well, we can use them. Don't huff them. That's bad. Oh, really? Oh. So I have a check question for you. when work is done on a system, for instance, compressing air in a tire pump, the temperature of the system does what? Increases, decreases, remains unchanged, or we'd have no idea?
Increase.
Why does it increase? Hang on. You're transferring energy. You're doing work on it, right? And that work is actually going into increasing the temperature, because if the volume, let's say, of a compressed air stays the same, we haven't really talked about that part of it yet, but if the volume stays the same, then the temperature is actually going to go up. So if you've ever pumped up your tire on your bicycle or whatever, and you feel the tire, it's actually a little bit warm. What is going to happen to this can here when I dust off my keyboard? Go ahead and feel that as it's going around. Okay? It's nice and cool. Yeah, and actually, all you guys are putting your grubby warm hands on them, it'll actually get warmer. But you want to shake, you want to do a little more shh. Go ahead. You can see, Andy, give it another little couple sprays there. Dust off something. There you go. Okay, why is the can getting colder is the question. And it kind of by the way, we were right about this one. Okay, the temperature increases, but why does the can actually get a little colder? It's, well, yeah, how? Let's think about this. This is actually a little tricky. So the air coming out of here is compressed in here, right? Starts out compressed in here, okay? And you push the little thing, and it goes shooting out and bounces into all these particles out here, okay? Which kind of press back on the air coming out of here, and it actually has to do work on the air out of here, outside. If it's doing work outside to the air around here, it's actually kind of heating up the air a little bit out here, right? What's it doing to the molecules inside the can? They're getting kind of pushed back and made to be cooler, cooler, cooler. Okay, that's actually what's going on.
The molecules are
now,
slowing down inside?
the molecules inside are slowing down. Yeah, they are slowing down. Now, they also are expanding into the more area in here as well, which also causes the temperature to go down because they don't hit the walls as much. But it's kind of a combination effect. So that's fun. If you turn, oh, it's actually shooting the actual whatever. Well, it's a liquid that's in it. Well, there's really not. I don't know if there's is there liquid in here? I guess there is. Yeah. But it shoots cold air, huh? Oh yeah, you're right. Now I'm gonna freeze my hand off. Yeah. Right.
You just got cancer.
Exactly. Exactly. Okay. All right. Easy check question. Kind of thing you'll see on your test. When a hot cup is filled with cold water. Now you got to think about it. But when the hot cup is filled with cold water, the direction of heat flow is what? From the cup to the water, from the water to the cup, random, or there is no heat flow?
Cup to the water.
Hot cup filled with cold water. Heat goes from cup to the water. Everybody agree? From the cup to the water. Okay? Not from the cold water into the fast. The heat flows from the hotter to the colder. Good. Okay, not too hard. Okay. I was actually, when I read the book here, I was surprised that the book went into this next topic. And here's why. It's actually kind of an advanced topic, although it's a cool topic. All right? This idea called entropy. Okay? Entropy is simply stated as how disordered a system is. In other words, how much disorder there is. For instance, if you have a house versus a pile of bricks after that house has fallen down over 150 years, which one's more ordered, the house or the bricks laying on the ground? The house is more ordered, okay? So we could say that there's more entropy, in other words, more disorder in the bricks than in the house, okay? And the idea of entropy, okay, is that whenever you get energy transforming into from one form into the other, okay, freely, when it does it on its own without some other effort coming into it, the direction of the transformation makes it more disordered, okay? And we get what we call an increase or greater entropy, okay? So what that means is, you remember earlier where we said that the first law of thermodynamics says you can never win the game because you can never transfer more energy than what you started with. It's always about conservation of energy. Entropy says not only can you never win the game, you're going to lose the game, right? Because if you pour water from that cold glass into the hot cup, yes, there will be transfer into the cup, but some of that energy actually gets actually released into the rest of the atmosphere. And in fact, what you're starting with is a nice hot cup and a nice cold water, which are two low entropy types of things. In other words, it's more ordered because you've got something that's cold and something that's hot versus kind of a mix that's all the same. You're not going to be able to spontaneously go back to the hot cup and the cold water again. It's not like you can take that. Let's say you pour cold water into a hot cup. And then you say, oh, I want to get back that cold water. You can't just pour the water back. After a while, let's say that you get some transfer of heat into the water from the cup. You can't just pour the water back into the bottle and have a hot cup again in cold water. It's just not going to happen again like that, right? That's why we talk about the direction of entropy is always a one-way street towards more disorder, unless you add energy to it. Okay, so for instance, yeah, go ahead, Tom.
Somewhere along the line, I can't remember if it was in class or if I read it in the book, somewhere it talked about like exhaust from a car.
Mm-hmm.
It's the same concept, kind of.
Well,
you can't
yeah.
get that energy back, or you can't turn that back into gasoline or oil.
Yeah, exactly. So Tom's saying that, look, gasoline is very ordered. Okay, it's a long string of carbon atoms that are really, really ordered. Okay, and the way they got that way was because the sun actually beamed down onto the earth, and then the plants took that sun, and the plants used the energy to create order in the structure of that thing. And then when the dinosaurs ate it and they turned into oil and so forth, that very ordered structure was still there. And then you go ahead and pour it into your car, turn it on, and your car burns it. It goes out the exhaust. That exhaust is much less ordered than the gasoline that you started with. Those long chains have been broken, and you got energy from it, so you can move your car, which is great. But those long chains have now been broken, and you're more disordered. Okay, so yeah, that's a good way. That's a good example, the one from the book. Okay, we restate the second law of thermodynamics. Nature tends to disperse from concentrated and organized energy states to diffuse and disorganized states. Again, hot cup, cold water, poured in there, you go from a nice ordered hot cup and cold water to an ordered system to kind of a disordered combined system. Okay? Energy tends to degrade and disperse, and we get this increase in entropy over time. Okay? All right, here's a question. Your garage, if you had a garage, your clue gets messier each week without cleaning it. In this case, the entropy of your garage is doing what? Increasing, decreasing, or remaining the same?
Increasing.
It's increasing, okay? Because that's the whole point of entropy. More disordered, more entropy. Okay? If your garage or your clue somehow became more ordered, okay, it would become less entropy and decreasing, yeah. Which isn't what happens. The only way that's going to happen is if you put energy into it to make that happen. Okay? All right. Specific heat capacity is the next thing we have to talk about. When you cook something, or when you heat something up, okay, the amount of energy you put into it, the amount of heat that you're adding to the system, goes into changing the temperature of that system generally, unless we do work. But some objects take much more heat to raise by the same amount of temperature. Okay? We kind of can call this, if you want, thermal inertia. In other words, some substances, you have to add a lot of heat to get them to increase in temperature. Some you don't have to add much at all. If you ever take something made of, well, like a metal pan, and you have a metal pan, and if it doesn't have a nice hand like plastic or wooden handle on it, and it's on the stove, you put it on the stove, and almost immediately you feel the heat in your hand, right? Do the same thing with like something with a wooden handle. Well, that's not a very good example because it's not a very good conductor. It's a good insulator. But if you do that with like water, you can boil water. You can turn the heat up on your stove, and you can keep your finger in the water for a good 1 or 2 minutes before you start getting like too hot, right? Do that with a metal pan, like just a metal pan, and put your finger on it. Instantly, you're going to start burning your finger, right? Because water actually has a very high specific heat capacity. Okay, also just called sometimes just specific heat. If you're eating a piece of pie, not that the pie here is ever warm, but if you ate a nice hot piece of pie, right, and you were to take that hot piece of pie, you know how you eat the crust, and the crust, you're like, oh, that's nice and warm, and then all of a sudden you get to that really hot filling, and you go, ah, and it hurts, right? That's because the pie crust has a low specific heat and actually doesn't actually burn your mouth because there's not as much energy there, okay, in that, for the same temperature. Okay? Hot Pockets, exactly. Hot Pocket, yeah, you're like, oh, nice Hot Pocket. You bite into it, and then your mouth dissolves because it's so hot. Yeah. One time, I actually, this was before I started teaching physics, although I have to say I was already an engineer, so I should have known better. I tried to make French fries. And here's what happened. I was living in San Diego, and I had gotten this, I had found this recipe for French fries, and I decided to make it. It involved cutting up all these potato slices and whatever. And then it said, take some amount of oil and pour the oil into the pan and heat the oil up to 300 degrees. Okay? And what I had done was I'd poured the oil into this tiny pan, and it was almost at the top of the pan. I'd poured it into this big pan, and it was only about that deep. And like, that's not going to go over all my fries. There's no way it's going to happen. So I get this tinier pan, and I pour all the oil in there, and it's like right from the edge of the top of the pan. All right? Okay, you can already see where this is going. And a horrible idea. Well, and then I turn the heat on for the oven, for the stove, and it starts heating up. And I'm thinking to myself, I have to get this up to it says 300 degrees, right? Well, you know how long it takes to get water to boil at 212 degrees? It takes like 15 minutes, right, or 10 minutes, depending on your stove. So I'm like, man, it's going to take forever to get this oil to 300 and whatever degrees. Well, no, but I leave it on, I crank it on, I'm just waiting, and I'm like, can't be hot enough yet, can't be hot enough. My roommate, who comes back and is from the South and her mom had cooked like fried foods her entire life. She's like, what is going on? And I'm like, I'm just cooking fries. She's like, that's way too hot. That oil is way too hot. I'm like, it can't be too hot because it's been on the stove for like, only 5 minutes or something. She's like, it's too hot. Turn it down. And she goes up to her room. And I go, all right. Well, I turn it down, but I don't really worry too much about it. Then I pour the fries in, and all of a sudden there's boiling oil all over the place. It's all over my stove. It's like literally catches on fire because of the stove, and I've got flames, and I'm putting it out. And whatever. Luckily, I was smart enough not to pour water on it because that'll, spread it. So I finally got everything. It took a week or two to get the smell of burning oil out of our house. What I had forgotten was that the specific heat of oil is much, much lower than the specific heat of water. So really, to heat oil up to 300 degrees only takes like 5 minutes. Take water like 10 or 15, right? And you can never get it up because it boils away. Oil doesn't even boil away. So that was my problem. I realized that. So anyway, the whole fries thing was ruined. I had to bake them. And baked fries are just not the same as actual fried fries. So anyway, it was a nightmare. But anyway, had I remembered, and I had a thermometer, but that's a different story. Had I remembered that oil is a much smaller specific heat than water, I wouldn't have cranked it all the way up for like 10 minutes. It probably would have been OK. Luckily, I did. Oh, the other thing about it, I did have some forethought. When I saw the oil like really hot, I realized that, well, I might as well protect myself in case there's splattering. So I got my leather work gloves and I put them on, and then so when I had to grab the flaming pan, it didn't burn me. So at least I was smart enough there. But next time, I've never tried fries since then. Because water has one of the highest specific heat capacities of anything, as it turns out, okay, this is actually a good news for certain places in the world. Anybody live in the West Coast right now? Yeah, you guys live in the West Coast. Most of the West Coast is fairly warm most of the year, right? Most of the West Coast is fairly warm. Here's why. Water stays relatively warm, okay? when the winds, which generally go from west to east, come over the nice warmish ocean, and I know if you live in San Diego or something, the water is cold, but really it's warmer than it kind of could be based on the latitude and everything. The warm air comes over the air comes over the warm water, gains a little bit of heat, or there's heat transfer into that air, and then it flows over the coast. Okay? And the nice ocean, warmish ocean breeze. And even in the winter, it's relatively warm. Okay? Same thing happens in Europe. I don't know if you guys ever noticed, but England is way up at the same latitude as Canada. But you don't see like pictures of like 12 feet of snow and polar bears in England, right? Right? The reason you don't see that is because it's the warmish air comes off the nice warm, or the ocean, right? And the Gulf Stream and whatever, and then comes and flows over and moderates the temperature of England, right? So that's kind of cool. The east coast of the United States doesn't get that benefit because the air here is flowing west to east still, and it doesn't pick up as much heat transfer, doesn't get as much heat transfer over the ground because there's not the ground itself, as the sun goes down, cools down very quickly. Okay, so it doesn't get as much over the ground, and therefore the coast doesn't get moderate. Now, right on the coast, it's generally fairly moderate. That's because you do get some winds back across. But if you're in the middle of this country, forget it. Because the middle of the country, North Dakota, you're like, record low again, negative 87 degrees in North Dakota, right? And you're like, why? Well, it's because it's not near enough an ocean to keep all that energy moderating in and out. Yeah, kind of.
How come Florida gets humid and California doesn't?
How come Florida gets humid and California doesn't? I don't know that, to tell you the truth. Maybe we'll figure that out when we get to the chapter on oceanography. I'm not sure. It's a good question, though. I'm not sure. Maybe because of the wind patterns down near Florida pick up a lot more water off the ocean. But it doesn't seem to make sense given what I just said, so I'm not sure. What's that?
Yeah, blame Castro for that.
Yeah, you should blame Castro for that. Not sure about that. OK, so the other one, we also use this idea of water having a high specific heat capacity for steam engines. For a steam engine, you boil water and you make it into steam. And that steam has lots of energy because it took a lot of energy to create that steam. When you release that steam through a turbine of some sort or some other release, a steam piston, you end up using a lot of that energy. And so it's a good way to transfer energy into the movement of your car. Okay? We talked about the moderation of the coastal regions. What's the other one they mentioned in the book? Bermuda. It's off the coast of North Carolina, right? It's like kind of way up here, right? Well, it doesn't get really cold in the winter. North Carolina gets kind of cold sometimes in the winter, right? Bermuda doesn't because it's in the middle, and it still gets the benefit of these ocean, like the, what's that? Because it's an island, and the water surrounds it and keeps it moderated. Mm-hmm. Good. OK, now we're getting into thermal expansion. As most substances increase in temperature, the molecules actually get a little farther apart because they're jiggling faster and they're bouncing against each other, and they get a little bit farther apart. Okay? Most substances expand when they get heated, and they contract when they cool down. Okay? Railroad tracks are a good example. If you lay them down close to each other on winter days, they expand and buckle in a hot summer day. Not so good. Metal lids on glass jars. If you ever have a glass jar and you can't get the lid off, right? Put it under hot water, okay? And then it'll be easier to get off. Okay? It's because the metal actually expands more than the glass does, and it'll kind of loosen it up a little. Kind of cool. Okay? I think I have some pictures here. There we go. There's the tracks. This is from your book. Yeah. I think that's from the heat. They say that that's from the heat. I'm not 100% convinced, but they say that's from the heat. The other one that you've probably seen on roads is these guys, right? See these little like expansion joints they're called? Yeah, it's on bridges generally. And what's going on there is the concrete would actually expand too much and break and crack if they didn't have these in here. So in the middle of summer, right, these are going to be nice and close together because the concrete on both sides is expanded. Okay, in the winter, they might be a little bit farther apart. Okay.
There's actually California, they have especially when earthquake occurs.
They use the bridges. They use this technique in California for the earthquakes. Yeah, I think these ones are specifically for the temperature, but yeah, they do have other things to make it so that when the earthquake happens, it doesn't fall, it doesn't break apart because of the earthquake. Yeah.
We've got a lot of bridges where I'm from, and we've got most of them have that concept to it.
Most of the bridges have this concept that you
And
see.
lots of times I have very low profile tires on my car, and I hate driving in the winter across the bridges.
Oh yeah, because of that. Yeah, that's a good point.
It hits, and
Yeah.
warped a rim.
Yeah, that's a good point. Anyway, it's there so that the bridge doesn't break, basically. Here's a check question. When stringing telephone lines between poles in the summer, it's a good idea to allow the lines to what? Yeah. When stringing telephone lines between poles in the summer. Yeah, I guess, so you have the pole there and you pole there. If you didn't let it do that, when it got nice and warm, or sorry, when it cooled down rather, what would happen? It would snap, yeah. So you don't want that to happen. So I guess if you look at the lines in the middle of winter, they should be a little less saggy than in the middle of summer.
Yeah.
That's the
I
idea.
would say allow ample space for birds.
Yeah, that's cool.
I think that's a good idea too. On Monday, we're going to get to birds on telephone wire, or birds on wires, and why they don't get electrocuted.
Okay.
So start thinking about that.
That's fine.
Okay?
Can I answer right now? So,
Sure.
they're not grounded.
No,
Okay.
not quite. It's not quite that they're not grounded. The question was why can a bird sit on a wire and not be electrocuted? In some sense, it's one way to. Yes, it's true they're not grounded. If they were somehow grounded, they would probably be electrocuted. That's not necessarily the reason that they can stand up there. We'll get to that on Monday, though.
They're not
Stand by.
necessarily on electrical lines, right?
No, let's say they're on a bare electrical line
Okay.
at 200,000 volts.
I think birds know which wire is live, which one's not.
They don't actually. They have no idea. They have no idea. No, they have no idea.
Oh, come on.
They don't know. No, they have no idea. No idea. OK, here's another question. Annette heats a metal ring that has the same inner diameter as the diameter of a metal ball, or just a little bit smaller. In other words, she's got this metal ball. You can kind of see it. She's got this ring, OK? And what it is, it's metal. Looks like this. Whoops. Well, terrible drawing. Metal ring like that, right? And she's got a ball that just barely fits in there. Okay? Just barely fits. Or it doesn't quite fit, but it just barely fits. If she heats up the ring, just the ring, okay, does the ball go through the ring or get jammed into it?
Fits through it. Number 3.
Fits through it? Why do we think it fits through it?
The ring expands due to the heat.
Well,
Just
yes.
told me that, Wales.
But, okay, I'm going to draw it here. But, okay, here I'm going to draw the ring here like this. Okay, like there's the outside part of the ring, and here's the inside part of the ring. Right? When it heats up, what's stopping the inside part of the ring from expanding inward and the outside part expanding outward? I don't know either. I've always wondered that, actually. But basically, well, boop. You guys are actually right. It does fit in the hole. I'm going to show you a little video of that in a second. When the ring's heated, all the parts expand. Okay? This means the expansion of the inner and outer circumference, inner and outer diameter, whatever it is, everything gets bigger. Not inwards, but bigger size. I know it's a little odd, but I've always found that an odd description. But I do have, let's see, the video here. Let me show you this. Control, delete. Okay, let's see. Try this again. I don't think this one actually has sound, but I'll plug it in anyway. OK. Oops. OK, so these videos are located here. Guess I could have just Googled it. There we go. Video by subject. Let's go down to Thermodynamics. And got a couple of them in here. Let's see. Here it is. Nope. Yes, here it is. Thermal expansion of metal ball and ring. Okay. It says the ball is just too large to fit through a ring. Heating the ring, however, causes the metal to expand. Whoops. You can barely even see it. Well, anyway, so right now the ball doesn't fit in. You kind of see that? And then you heat the ring with a cool blowtorch.
That's what most jewelers do. They size up or size down the ring.
Do they really? Oh, then they put a piece of metal inside that keeps it at that size? I didn't know that. Jewelers do that. I didn't know that. How do they keep it from burning? Or like putting carbon on the end? Oh, they do. Okay, and there you go. So now it's hot. Notice, whoop, right through. Just like that. Yeah. And you can actually leave it in there, and then it'll cool down and won't come back out. Done that before, too. OK. Let's see. There's another one here. Let's see. Hang on. Oh, we're going to get to this one. I'll put it back here. OK. All right. OK. All right. Now we've got the expansion of metal itself, which is kind of cool. We've got this thing called a bimetallic strip. Part of the strip is made of brass. Part of the strip is made of iron. Those two pieces are welded together. And then when you actually heat it, the brass expands more than the iron does, and it bends. It goes and bends. Okay? When you cool it, it's the other way around. It bends the other direction. Okay? And it's like this. Does it go? No, I don't think so. Maybe it does. It might. Let me show you what Hewitt has to do this one. Let's see how a thermostat works. So this is actually this is what we kind of talked about earlier, how the thermostat works. There we go. When it's wet?
Hi, gang. Thermal expansion time. Here I have what's called a bimetallic strip. It's a strip of metal consisting of two kinds. Brass on one side, steel on the other, welded together. I'm going to heat it up. Looks like it's bending. It's bending because one side's expanding more than the other. If I take this and turn it into a coil and heat it up, it would shrink. Or cool it, it would expand. That would be a thermostat.
That's kind of cool, huh? The other place that I've seen a bimetallic strip, which is in grandfather clocks. You know how grandfather clocks have those long pendulums on them that swing back and forth? Well, we didn't really talk about it the other day, but remember that video of the guy with the bowling ball that we showed? In that video he has, which is on the website, he shows that the length of a pendulum is what matters. It doesn't matter how much weight is on it for how fast it swings back and forth. It just matters how long the weight is, or how long the pendulum is, which is kind of cool and which kind of makes it nice if you're trying to do something like time something. So if you want your grandfather clock to be nice and even, click every second it goes one click. If you want it to be true, you want that pendulum in there to swing at exactly the right rate the entire time. If you live in a house that cools up or heats up and cools down, well, the rod, which is made of metal, will do what? Contract and expand, and then it gets longer and shorter. And what happens to the time if it gets longer? You can guess. If it's a longer one, it takes longer to go back and forth. If it's a shorter one, it goes back and forth faster. So if you've got a house that does that, well, your grandfather clock will be wrong. So what they do is really clever. They put metal together like a bimetallic strip, except they put them side to side like this and kind of like scatter them in there in the pendulum. So the pendulum actually, if it's kept from actually lengthening because one piece tries to contract, the other piece tries to expand, and it kind of they cause a lot of forces in there, but it actually keeps it from expanding or contracting, and so so it doesn't change the time. Yeah, so it's pretty clever, pretty clever. Okay, all right, so that's a bimetallic strip. We talked about, well, we haven't quite mentioned it yet, but here, water is actually a weird one. Okay, we did mention this a little bit earlier when we talked about water being on the 4 degrees at the bottom of a pond. Water is different. Okay, when it gets below 4 degrees Celsius, right, it actually, as it gets lower and lower to 0, it expands. As it becomes ice, it expands, which is odd. Okay, and what's going on is inside the water, all these particles which are bouncing around here, when they get into water form, or ice form rather, they create these actual, what are they called? Crystals, I guess, which are much bigger in size. And it's actually the changing into that form that actually makes it expand. Okay? And so therefore, ice is actually much less dense and is bigger, so it expands. Kind of cool. It only happens from 0 to 4 degrees that's the case. Okay? Going from 0 to 4, it doesn't expand, it actually contracts. Okay? At a temperature of 0 degrees, water is less dense than the other water, the water that's slightly warmer. Okay? So it actually rises, and therefore you end up with the water, or the ice, on the top of the water. Okay? Water at 4 degrees, smallest volume, greatest density. Something's in a pond and it's the greatest density in the smallest volume, it's going to sink to the bottom. And therefore, at the bottom, it's going to be nice and 4 degrees Celsius. Okay? And same thing with the water, when it freezes, it's the largest volume and the lowest density rises to the top. Okay? I think I have the picture they show you in the book from that. Oh, this is one of the pictures. You're being pulled? OK. The video will be online probably tomorrow afternoon or something, evening. Okay. All right. This is kind of just a diagram of what's going on. Here's 4 degrees right here. It's nice and small, nice and dense, sinks to the bottom, and it's the volume here is the smallest. As you get a little cooler, right, you expand and you get to there. Now, once you get even cooler, you do start expanding or contracting again. Okay, but as you get as you go from 4 and start getting bigger and bigger, you will expand. Okay, but 4 is that magical minimum there. Okay, and this graph kind of shows that too, but it's pretty cool. And I do think I have the fish in there too. No, I don't have fish. Maybe I don't. Check question. Take 0 degree water. When you heat it, does it expand or contract? The first thing it does, when it goes from 0 to 4, 0 and gets 1 degree, 2 degree, 3 degrees, does it expand or contract? Remember we just said it actually contracts, gets a little smaller, and that's why it sinks to the bottom of the pool or a pond or whatever. Okay? They have this interesting explanation here where you get the melting of microscopic slush crystals. Okay? It's kind of odd. Water continues to contract until it reaches 4 degrees Celsius. With further increase, it then expands. Okay? So that's the check question there. Here we go. Now, this is what we talked about at the beginning. The fact that water expands as it cools could be the reason life on Earth exists. I made that up, but I mean that wasn't in the book, but I actually tend to believe it. We think that life began in the oceans, right? The way it works. If we had this freezing all the way down to the bottom of the ocean, right? Well, all that life in the ocean most of it would die. Not that we don't have bacteria and things that can live in ice, but it probably wouldn't be great for things like fish, right? They don't do so well if they're frozen. And so the fact that we get this layer of ice up here and the nice cool but not freezing water below it probably led to the ability for life to continue to evolve. One interesting thing about this is the ice actually acts as a nice insulator as well. Okay, so it also it doesn't actually let this heat up too much in the winter either. So it's kind of cool. But anyway, there's your little fish. He's happy because he's at 4 degrees Celsius or above, or not all the way to 0, and he doesn't get frozen solid. Yeah?
It might be a little off topic. Have you heard the term denaturing?
Mm-hmm.
What does that mean?
I have heard of denaturing. Honestly, I don't know enough about it to be able to tell you what it means. Like you mean denaturing alcohol and so forth?
Or like anything. cook stuff,
It's
egg will go from like, you know, jelly or whatever, and cook it long enough to turn solid.
yeah, so it's something to do with the proteins. I'm not sure. I'll have to look it up. But you could also look it up too. Look up denaturing. What does it mean to denature? Then we'll compare notes tomorrow. How's that sound?
There's a YouTube video.
Probably is a YouTube video, yeah. Okay. All right. So just a review here. Cooling of water in winter, the water becomes more dense and sinks until the whole pond is 4 degrees Celsius. Then you get more cooling, and the top of the ice freezes. There you go. Okay. Let's see. Heat transfer and change of phase. Okay, this is the next chapter. So we're actually finished up chapter 6. Now we're going to run into chapter 7 here. Heat transfer and change of phase. This book actually doesn't quite go into change of phase the way I thought it was. I'm going to mention a couple things about change of phase that I think are interesting that the book didn't really talk about. But we will first start off and talk about actually transferring heat. Okay? 3 ways to transfer heat: conduction, convection, and radiation. Okay, we'll talk about all 3 of those in that order. Okay. Conduction is how when you transfer internal energy by the molecules themselves colliding and the electrons colliding with other molecules in the substance or in one right next to it. Okay, it primarily happens in solids, and it primarily happens in solids, and you can see it happening or you can feel it happening when you do things like if you were to take a nail and put it into a block of ice, you could feel that nail getting cooler. Okay? Same thing when we talked about if you have a pan and you put it on the hot stove, the metal part of the pan gets hot pretty quickly. That's through conduction. Okay? The hot stove touches the bottom of the pan, and throughout the pan, the conduction of heat goes through the pan to heat up all the parts. Does that make sense? It's conduction. You guys probably seen this one a number of times. Okay? How does insulation now affect conduction? Anybody ever had to lay this fiberglass insulation? Do you have to wear gloves and like it's
like fiberglass.
well, that's what it is. It's fiberglass, actually. Yeah. And I don't think I have a check question in here about that, but I'll ask the question anyway. But in this case, does insulation actually prevent the flow of internal energy?
Yes.
Kind of. The answer is yes to an extent. It slows it down. No matter how much insulation you get, you're never going to get perfect insulation. Okay? I suppose the only almost perfect insulation would be if somehow you had a vacuum with no substance in there at all. You wouldn't get any conduction. You would get radiation, which we'll talk about later. You wouldn't get any conduction. But insulation actually slows the rate at which energy flows back and forth. Okay? Fiberglass, which is what Kenneth just said, is what this stuff is made of. This is fiberglass insulation. Okay? It's basically very puffy, but has little pieces of glass kind of put inside it, fibers of glass. It's terrible if you get it in your hands. Notice this guy's wearing gloves. Okay?
Or breathe it in.
Whoops. Or breathe it in, yeah. Yeah, no kidding. And it slows the transfer from the outside to the inside. Now, glass is actually it's a relatively good insulator, but it's not as good as air. Why might they put glass in here? Any idea?
To conserve the energy,
Because
conserve heat.
Well, kind of.
Winter and cold and
Well, yeah, but why do they use glass and not just like the air?
the way the glass doesn't take, if it has a low heat capacity.
Yeah, I don't know if it has much to do with heat capacity necessarily, but it definitely has to do with the fact that the glass actually traps the air in there. The air can kind of bounce between all the different particles of glass in there, and it traps the air in there. So it's really the air that's doing the most insulating, but it's because the air can't flow right through. If you didn't have the glass in there, the fiberglass in here, you'd actually be able to get more air flow through, and then that doesn't help you, because that's actually using convection, which we'll get to in a minute. So what it does is you want to trap as much air in there, because air is a very good insulator. You trap that air in there, and then the heat can't go from the hotter part, which might be inside your house in the winter, to the outside, or in the summer, the exact opposite. It keeps the hot air from outside transferring heat into the inside. Okay? Yes, exactly. You get some conservation of energy in that case. And so that's why we use this insulation. But it doesn't stop it. It just kind of slows it down. Okay? Anybody ever tried walking on hot coals? I've never done this. I've juggled flaming torches before, but I've never walked on hot coals.
I just walk to work in the morning.
What's that?
Just walk to work in the morning.
Yeah, just walk, around here in the summer especially, walk to work in the morning. But the problem with that is that, well, mud, I guess. Mud, I don't know how good a conductor of heat mud is. But this guy, these are red hot coals of wood. And wood happens to be a very poor conductor of heat. Doesn't matter how hot it is, it's going to have a hard time conducting heat from the coals, even though they're really hot, into his feet, as long as he walks quickly enough. Trust me, he's not standing there hanging out, because then he's going to get burned. But if he's walking boom, 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 pretty quickly, there's just not enough time to transfer the heat from the wood into his feet.
So you won't get blister or something?
What's that? He won't get blisters from that if he goes fast enough.
How would I burn myself with iron every time I hit it?
Ah, think about this. An iron is made of metal. Metal is a very good conductor of heat, and therefore, the instant you touch your hand, you burn it. Yeah, yeah. This is why they don't make irons out of wood. Right? You'd never be able to like get the heat transferred out. Iron, well, you can iron with a hot rock maybe. Rocks are probably better, but yeah, the wood definitely.
Most of the pots, and they have like wooden handles.
Pots have wooden handles, exactly. And that's exactly right. Yeah. Yeah, because of the fact that you do that. As we said, air is not a good conductor. It's a good insulator. If you are taking a pizza out of your oven, right, you can reach into your 400-degree oven, grab the pizza. I mean, you have tongs, but if you can, let's say there's a wooden handle on. Let's say you're cooking something in the oven and it's got a wooden handle. You can reach in there, pick it up, put it outside, and you'll be fine. Don't touch the side of the walls of the oven. You'll burn your hand. Right? Same thing. Okay? All right, so that was conduction. Things need to be touching for conduction. It's generally internal to an object, and that's how heat gets transferred within a solid object, generally. There's also convection. Okay? Convection is when a fluid, and remember, fluids are either liquids or gases. Talked about that last week. When a fluid is kind of moving amongst, the molecules are moving amongst itself, and the heat gets transferred from one part to the other through that fluid motion, that's when we've got convection. Okay? Convection happens in the air in a house. Okay? Convection happens when you heat up a pot of water. The water kind of goes up and down. Let me see, where was the convection? It's in one of the Hewitt videos again. You can see convection, you can see convection in one of these videos. Let's see, chapter 7, videos. And let's see, air is a poor conductor. Let's look at this one first. Let's look at air as a poor conductor, and then we'll look at a couple others here. All right.
It turns out that air is a good conductor or poor conductor. It turns out it's a poor conductor, and aren't you glad? Because what if air were a very, very good conductor? How would you feel all the time? Begins with a C, ends with O. Put it together again. You would feel cold. Let's suppose the air was good conducting is like a piece of metal. You ever stand in the mud at home and lean up against a metal door? Whew, it's cold to the touch. But that metal door has the same temperature as the air around you. So be glad that air is a poor conductor and a good insulator. In fact, when you want to keep yourself warm when you're going to go camp and that sort of thing, don't you get a down-filled sleeping bag? What's all the down for? It's holding air in one place. It keeps the air from circulating. And that down will just hold the... How about animals? You wonder about the animals. How do they make it up in the snow-covered mountains? They're covered with fur. And that fur puffs up, and guess what it holds inside? Begins with A, ends with R. Air. And that air is a very, very good insulator. So most of the things that keep you very, very warm in a cold climate, like that which insulates, like styrofoam, yeah? Or spun glass, or things like that. They're all what? They're things that hold air. See these thermal underwear they have now? The thermal underwear, you look at the thermal underwear, and all this is like a net, like a fish net, and you put that on, and that's going to keep you warm? But over that fishnet underwear, you put a regular t-shirt. And now what's trapped between your skin and that t-shirt? Begins with an A. All right, ends with R. Air, okay? And can that air circulate? No. If the air warmed up and just went away, then you get cold again. See? But it's all held there by the little netting. That's what it is. When that stuff first came out, I looked at that and said, what? Because, who's going to keep you warm, honey? And they show you something with all these holes. They say, all these holes? That doesn't sound right. But wait a minute. I know what that is. It begins with a P. I mean, it begins with an F. What is it? Well, you don't be knowing. Physics.
He's a little odd.
It's crazy.
Yeah, but he's kind of smart too. Okay, let's see. Where was it here? Was it boiling? No. Coal walk? One of these ones. Oh, I know. It was the other one. Hang on. Let's look at this one, and then we'll go over the other one. I do know where the other one is.
So some things conduct better than other things. Piece of wood, very, very good insulator. This wood's a good insulator at any temperature.
We already kind of talked about this.
This wood is a good insulator even if it's very, very hot. You ever reach in a frying pan and pull out of the frying pan, even if it's up to 400 degrees Fahrenheit, you're going to cook some food or something, you got a frying pan in there and it's all iron? Ever be reaching in with your bare hand and grab the iron pan? If you ever have, you can show that today, you'd be tattooed, right? You're going to burn yourself, isn't that right? But could you reach into that oven and grab a pan if it had a wooden handle and grab it momentarily? You can do that. You can do that. You know why? Because that wood is hot. It has the same temperature as the metal.
Okay, we already
But
saw
not
most of this.
very much energy is going to conduct from the wood to your hand.
Okay, we already saw it. Now I want to show you this one. Oop, doesn't matter. In this other one I'm about to show you, this is kind of cool. They take water. We'll see in a sec. They take water, and of course it already started. Ruining my thunder there. Okay. They take water, they heat it up, but they put a light on it that projects onto a screen. And as it turns out, we'll get to this in a couple weeks, when warmer water actually has a different, lets light go through it slightly differently. So if light's being projected through it, you can notice where the hotter water is. And watch what this does. Okay. Okay. So they're now heating up water. They've got a bright light through it. Okay. You can barely see the water. This is actually the water over here. Notice what happens when it starts heating up. That's the convection. Okay. Those little lines in there are just the hotter water.
What, you got a resistance in the water?
I think it's just I think it's probably just a heater coil of some sort. Yeah, yeah. So isn't that pretty cool? And by the way, we know why the hotter water, which is less dense, because it's water and it's not at that kind of weird thing, but it's less dense. Why does it float to the top? Starts with a B, ends with Y. We learned about it last with buoyancy, right? That hotter water is less dense, so it has more buoyancy and goes to the top. Okay, there you go. All right, you can see the same sort of things with smoke in a room. All right. Okay, where were we here? You can do it. You can do it. I guess you can't do it. Hold on. Oh, there we go. Oh. Almost. Come on, I know you can do it. There we go. All right. Okay, so that's convection, like that. Okay. I wouldn't necessarily try this at home unless, well, you could try this at home. Got a pot here. This is like a steam pot. It's got this little thing on the top. You can do it with the regular tea kettle if you want, where the steam comes out. Notice where she has her hand up here. it's actually relatively cool up here. What's going on is the air, or the water, is coming out of the pot. Notice here you can't see that little any steam right here. It's hard to see around the corner. You can't see that. That's because that's actually the steam. And that's the really hot, over 100 degree or 100 degree steam. And then it expands and it cools very quickly. And that's why it ends up doing this, okay? You do get that cooling effect. We're going to talk about what happens, how we get other cooling effects in a little bit for the objects losing heat. So cloudy region, not so hot above that. Yeah.
Now,
Tom.
when you like the vapor that you see, isn't most of that the moisture in the air condensing more than what's coming out of the pot?
I don't think so.
I saw that or read that somewhere.
That may be true. I'm not sure. I don't think that that's the most. I think most of it is the water that's coming out there. I'm not sure though, because that really is steam right there, and steam has there's a lot of energy in steam, but I'm not sure. Okay, let's do this. Let's take another break right now, because I know I'm keeping you, and come back right at 7:30. Good, thanks. Okay, so we talked about convection, which is the second type of the way heat gets transferred. And convection is a bulk transfer. In other words, big pieces of the fluid are moving back and forth, transferring energy and transferring heat between the different parts of the substance. The third type is called radiation. Now, this is not radioactivity. Okay, we're talking about electromagnetic radiation, which is what comes out of your cell phone or your microwave oven, or things that are, or even you actually emit infrared radiation. That's why the SEALs can shoot you in the middle of the night, because they have infrared goggles that pick up on that, your signature. Okay, so this is the types of things we're talking about: radio waves, infrared waves from like fires and things. And by the way, infrared and visible light comes from a fire. And then you have regular old light waves, which are visible light waves, I should say. Okay, that's what we mean when we talk about radiation. So every object that's not at absolute zero, and we already said objects can't get to absolute zero, so every object radiates energy. Okay? The sun radiates solar energy. The Earth actually radiates infrared energy. Okay, energy at the infrared wavelength. And you can kind of see here this little picture. So light waves that are short wavelength, like the ones you can see are generally pretty short, they actually have they actually look a little squigglier, if you will. We'll get into this when we talk about waves. Then the big, nice, long wavelength infrared radiation from the Earth. So basically the sun beams down on the Earth with light rays, which have high frequency. The Earth actually re-radiates energy at lower frequency. And this is going to become very important in a few minutes when we talk about greenhouse effect. Okay? But you also radiate infrared radiation, okay? Which is part of the reason that you constantly have to have some form of insulation, or you will cool down too much. Okay? If you're in a cold room. That's why when you, there's two reasons when you have a blanket. Hey, have you ever seen at the end of anybody run a marathon in here? Or I've run a couple marathons. It's kind of cool. The little space blanket they give you at the end of a marathon is silvery, right? And you put it on. Yeah, it's made out of like mylar or some sort of very reflective material. And that reflective material reflects not only light waves, but also infrared radiation. So when you put it on your body, it's really thin, and it's like aluminum foil almost, like that thin, but more stiff, or rather more malleable. But when you wrap it around yourself, it keeps you warm because the infrared radiation that comes off your body gets re-radiated back onto you again. So it kind of keeps you warm that way.
It like traps the heat?
It traps the radiation heat, yes. Yep. Not so much the convection. It also keeps the air from going past you and drawing off some of that heat as well. But it definitely keeps you warmer because it bounces the radiation back toward the waves back towards you. So it's kind of cool.
Why would you want that? Wouldn't you want to cool off?
Good question. if you are, you do want to cool off, but you're radiating so much energy because you've just run for 3 hours, 4 hours. You just run 26.2 miles. So your body is like in a state where it's like, I got to get rid of all this energy. I got to get rid of all this energy. So if you stop running, you'll actually cool down very quickly if you don't have that on. And so they want you to stay warm enough with those. And if you run the Boston Marathon, which I ran a few years ago, it's very cold out generally. Sometimes. Some years it's freezing. The year I ran it, it was like literally snowed during the race. And then the year, 2 or 3 years before, it was 78 degrees or 80 degrees, and no, not so good. Much better the year I ran it. Better to be cooler than hotter. But yeah, good question about why you want that to happen. So we talked a little bit about this. The cooler you are, the longer the wavelength or the shorter the frequency your waves are. So cool, nice long wavy things. Medium, a little less or a little more wavy, and hot, really wavy. In other words, higher frequency, shorter wavelength. Low temperatures emit low, long frequency waves. That's the infrared stuff. Medium, a little more medium, and a high temperature emits primarily high frequency waves. The higher the frequency, the closer you get to visible, and then you can go over visible like X-rays, but you get to visible, and the visible light is from very hot sources like the sun or the light bulbs. Yeah, the bears. Any material actually does absorb and then emits radiation. Okay, radiant energy. When you absorb more than you emit, you actually increase your temperature. This kind of makes sense. When you emit more than you absorb, I don't know why I can't say that. When you emit more than you absorb, your temperature goes down. Okay. We kind of know this by how we paint our houses generally. Okay? Good absorbers and good emitters are actually dark, which is interesting. Poor absorbers and poor emitters are light in color. Now, the sun, incidentally, happens to be a very good emitter of light. Yet you look at it, and it's extremely bright, right? Does that mean that it's light in color or dark in color? It's a good question. I tell you what, you try beaming another bit of light off the sun and telling me if it's light or dark. The sun itself, because it's an emitter and what you're seeing is what it's emitting, you can't tell whether it's dark or light. The sun actually is very dark if you were to somehow get rid of all the light that was coming from it. Because it's matter. And it's matter, the fact is, it's a very good absorber and emitter of light. The sun is. Okay? But we know that this dark picture is going to be a good absorber of light, but also a good emitter of light. Okay? But the reason we don't see it, like it doesn't reflect light necessarily, but it emits light, which is slightly different. Okay? Something can emit energy without reflecting it, like you do right now. You're not necessarily reflecting things. Okay? But if like Andy's wearing a white shirt, that's a better reflector of light. It doesn't absorb so much. And James is wearing a dark shirt, right? So you wouldn't want to wear that in the middle of the summer out in the sun, right? Because it absorbs a lot of that energy. Okay? It does radiate it off too, but it absorbs it.
I questioned myself when I was deployed in Iraq.
Oh,
Other different countries, how the women are wearing the burqa and all these black dresses, and versus the guys are wearing white togas.
Yeah, that's a good question. They must be pretty warm.
Feeling,
Yeah, if they're wearing dark clothes in the summer, in the hot, yeah, they must be pretty warm in there. Yeah, it might be the type of material too that actually.
Another thing is they're loose fitting. So
That's the other thing. Yeah, if they're loose fitting clothes, a lot of.
it's still dark color, and it's gonna.
It still does get warmer. I'm sure it still does get warmer. Yeah, I'm not sure why they do that, but yeah, cultural things. Yeah. So whether a surface is actually a net absorber or a net emitter, in other words, if it absorbs more or it emits more, actually depends on the temperature, if it's already above or below the temperature of its surroundings. Why? Well, go back to the first law of thermodynamics, or rather the second law of thermodynamics, which says heat always transfers from hot to cold. So if you're colder, sorry, no, hot towards cold, right? Heat always transmits from hot to cold. No, hot to cold. Yeah. You can always think of it this way. If you were at absolute zero and you could get rid of, you can't get rid of heat at absolute zero because there is none to get rid of, and you couldn't go, you couldn't give it to the hot part. So anyway, back to this: a surface that's hotter than its surroundings is going to emit more energy than it absorbs, just because of that law, the second law of thermodynamics. So as colder will be a net absorber and tends to get warmer. Now, whether it's good or bad at that depends on the color, like we talked about in the last slide here. Okay, but if it is cooler, it will be a net absorber. It'll tend to absorb more energy. Okay. All right. Here's a question: if a good absorber of radiant energy were a poor emitter, its temperature would be what? Lower, higher, unaffected, or none of the above? If it was good at absorbing, but poor at emitting, it would absorb more and not, it would be higher, right? So is that possible? No. Why isn't this possible? Yeah, if for some reason it was better at absorbing than it was at emitting, right? It would tend to stay warmer than the surroundings. Can something on its own stay warmer than its surroundings? No. Now, humans can, right? We do that right now. You're all warmer than the surroundings. How do you do that? By doing work, by burning calories, right? Right now, I know you're not at the gym, but you're actually burning calories right now. Now, it's not necessarily enough because you probably ate too much at Child's today, right? But you are burning calories right now. So that's the thing. So again, if you're a good absorber, you're also a good emitter. Okay?
What is it? The average male needs 2,000 calories a day?
I think so. The average male needs 2,000, something like that. Maybe 2,500. Yeah, I don't know, something like that. Yeah. Darkness is sometimes due, often due, to when light goes into something and bounces around and doesn't end up bouncing back out towards your eyeballs. Okay? In here, I think if you all look below the podium there, that there's that little box in there. Isn't it dark in there? It's darker in there than anywhere else. I don't know if you can see it from over there, but if you peek in the box there, Nicholas, right now, under the thing, you'll see it's dark in there. What's going on is it's exactly that. Light is going in there, and it's bouncing around in here so much that it's not actually coming back out to our eyes. So it doesn't look like it's light. So that's part of the reason it's...
So if we had like a mirror in there, it would light up?
If we had a mirror in there, it would be lighter, yes. Yep. Yep, absolutely. And remember, good reflectors are poor absorbers. Good things that reflect well are bad at absorbing. It's always the opposite in that case. Yes. Yep. Okay. All right. Which of the following does not emit radiation? A fluorescent lamp, incandescent lamp, a burned out incandescent lamp, or none of the above? Does the burned out incandescent lamp still emit radiation?
Yes.
Can you see it? No. Right? So certainly it's none of the above. Everything emits radiation, but some things you can see the radiation and some things you can't. Okay. All right. Okay. Good old Newton is back. Okay, Newton did a lot of stuff, so he pops up a lot.
With the apple pie this time.
This time with an apple pie instead of an apple, right? So Newton's law of cooling actually says that the cooling of an object is proportional to the difference between the object and its surroundings. Okay? In other words, things cool faster if the surroundings are cooler to begin with. And that just makes sense intuitively, I think. Okay? What's interesting is, let's say you did this. Let's say we took a cup of coffee. Okay? Let's see if I can phrase this right. You take a cup of coffee, and you want to cool it down enough so that you can drink it. Okay? So you want it to be cool enough so you can drink it. If you pour some milk into it, it doesn't quite cool down enough. You still have to wait. Okay? Is it better to keep the milk out and pour the milk in a little bit later, or to pour the milk in immediately if you want to drink the coffee the fastest? Like if you want to get it to a point.
Later, because the cup is losing heat with the energy that is evaporating.
Okay.
That's fine.
So Nicholas says it's later. You add the milk near the end, and then that's the best way to do it. What do you guys think? You think you'd wait as well? Okay. Anybody think that you'd want to pour the milk in right away? Get it down a little more to the temperature?
Does the temperature drop at a constant rate?
Does the temperature drop at a constant rate? No. It's proportional to how much the temperature around it is. So at first it drops more than later.
Okay, then wait for the milk.
Yeah, absolutely. Yep. So you do actually wait till later. Turns out we could probably do this experiment if I think I might have enough things, but you do that. So while you're at that higher temperature, you're going to drop much faster to a temperature that's low enough so that when you pour the milk in, you'll get low to where you can drink it. Otherwise, you pour the milk immediately, you have to wait a little bit longer because it's down less temperature, but not all the way to the bottom. So yeah, so very good. Very good. OK, let's see. Warmer house more quickly leaks thermal energy to the outside than a cooler house. OK, here's another question for you. Is it better to leave your air conditioner on low when you leave, let's say you were to do this. Tomorrow, you leave your clue. Okay? You want it to be, you want your, let's see, how am I going to say this? I want to phrase this one right. Well, part of it's about conserving energy. Yeah, here we go. So here's the deal. Either you turn your air conditioner off when you leave completely. Then when you get home, you turn it back on, and it takes some time to warm up or to cool down to the temperature that you want. Okay? Does that waste more energy than leaving it on a relatively small, leaving it on but at a cooler, a warmer temperature, and then just turning it up a little bit when you get home? Which one's the best way to do it? You think leaving it at a steady temperature keeps you, in the end of the day, you turn it up and it only has to go up a couple degrees instead of doing it all at once?
But it depends how long you're going to be gone. But
let's say you're gone for like an hour or two.
Oh no, it's better to keep it on at low temperature.
Think so?
Absolutely.
Let's go back to Newton's law of cooling for a second. So if you turn it off, and it's kind of the other way around in this case. It's kind of Newton's law of heating, and it's kind of the opposite of this in some cases, in this case. You turn the air conditioner off, and then it gets nice and warm. And you turn the air conditioner on, but all day, the air conditioner is completely off, not doing anything. Okay? And then at the end of the day, you turn it on, and it does take like 15 or 20 minutes to get down to that cool. But the amount of energy you're using to cool it at the end of the day is actually much less than if you left it on. Because that whole day, you're losing energy to the, well, I guess in some sense you're gaining more energy from outside all day because of the transfer in and out of your house. It's kind of better phrased if it's the other way around. If it's winter, it's easier to think about if it's winter. Do you leave the heat on? Is it better to leave the heat on at a certain low temperature or turn it off all the way? Now, you're never going to turn it off all the way if you live in a cold area because pipes will freeze. But it would be better for money-wise and energy-wise to leave it off of the day and then turn it on. And then even if you're gone for all day or even an hour. Yeah. Well, I see what you mean. You were saying because an hour is a short amount of time. Let's say it was much. The time does, yeah. If you're only going to be gone for 15 minutes, there's no point. It is not going to make much of a difference. But if you're gone for many, many hours, the transfer of heat is going to be greater. It's going to happen all day. It's kind of what goes back to that idea of insulation doesn't really stop the transfer, just slows it down. It's still going to happen. Okay. All right. So that's that one. Newton's law of cooling. Okay. Here's the greenhouse effect. Remember how we said the sun is high frequency wavelengths, like visible wavelengths, and the Earth re-radiates at much lower frequency? Turns out this happens in a greenhouse This is why this is called the greenhouse effect. Okay? If you get short wavelengths go through glass, longer wavelengths bounce off glass. Same thing happens in our atmosphere. The short wavelengths from the sun go right through the atmosphere. The longer wavelengths that get radiated off bounce off the atmosphere. So here's what happens. You get lots of energy from the sun, and it comes down, and then it bounces off the Earth and re-radiates as much lower wavelengths, but then bounces off the atmosphere and bounces. You get lots of energy in. It's like you can go in, but you can't. It's like those roach traps. They're one way. You know, the radiation can come in, but it won't get radiated off as much. Okay, so that's what's going on with the greenhouse effect. Okay, similar to what happens in the actual atmosphere. I think I might have a couple more here. All things radiate at a frequency that depends on the temperature. The sun is very hot, radiates visible light. Okay? Transparency of things depends on the radiation, the wavelength. So glass happens to be transparent. The air happens to be transparent to the highest wavelengths, and it will bounce off the lower wavelengths. Sorry, the other way around. Transparent to the higher frequencies, and will bounce off the lower frequencies. It's kind of cool. Okay, and that's how climate change happens with the greenhouse effect. Okay, absorb energy from the sun. The longer wavelengths get bounced back, and part of it's bounced back. Not all of it, but part of it is. And then you end up warming up, which is actually a good thing, because you do want to keep some energy, especially at night. We talked about this last week. When at night, the sun's not beaming on that side of the earth, it cools down, but you don't want it to, all the radiation to radiate away, or you'd get very, very cold. Happens in the desert more, because the desert happens to radiate better. That's it. Okay, another one here. What causes the climate change? Terrestrial radiation absorbed by the atmospheric gases get re-radiated, re-emitted, but they bounce off the atmosphere. That's kind of cool. Okay. All right. Finally, phases of matter. Okay, and this is the part that they don't describe this as much as one thing that I'd like to describe a little more. Matter exists 3 phases: solids, liquids, gases. Okay. Ice is the solid, liquid, and plasma. Yep, you're right. So I guess you're right. So 3 common phases, and then the 4th is plasma, which you don't really see on Earth that much. Okay. Energy gets transferred when you change phase. Okay. When you're going from here to here, you actually absorb energy. Okay. When you go from a solid to a liquid, the liquid's absorbing energy. When you go from a liquid to a gas, the gas is absorbing energy. You release energy going the other direction. So this is interesting. Ice, as it cools, releases energy. Actually gets some energy actually goes out of the ice when you are cooling it. Okay. Here's what's going on in a gas when you are changing the phase. There's a little border here between where the substance is a liquid and the substance is a gas. And evaporation happens when these little molecules get enough energy to kind of jump off the liquid level and end up having enough energy to become that gas. If they condense this gas, they go back into the liquid phase because they lose energy and end up in the liquid phase. Okay? So they gain energy going here, and it's a cycle. And if you're in the process of adding heat, you're going to make much more of these molecules faster and more potential to jump off than to come back down. Okay, so it is a cycle. But if you're adding heat over here, you can actually get it to more particles go into this side of the picture, and so you end up boiling the water, okay, turning it into a gas.
It's humid during the day, and then at night everything condenses and goes on the ground.
It's exactly why it's humid during humid during the day, and then at night you get the dew on the ground because it's doing this. It's cooling down, and you're getting the condensation, which is the dew. Okay. One thing they don't talk about in the book here, as this is happening, let's say this is water. What temperature is this water going to be at? if it's in the process of well, sorry, if it's in the process of boiling, not evaporating.
Okay.
But let's say it's actually changing phase into, let's say it's boiling. 212 Fahrenheit, but in Celsius it's 100 Celsius, right? And if that's the case, it never gets above 100 until all of the liquid has turned into the steam. Okay? And that's because all the energy is going into this phase change, not into heating up the extra steam. Okay? So the steam you have to kind of get up to that place where it's more than, everything's already boiled before that can be above 100 degrees.
Eventually, this water is going to disappear.
Yeah, eventually it'll all be gas. And if you were in a container, it'll all evaporate once you, right. Yep.
Water.
Yep.
The pot, and I have the lid.
Yeah, there's your pigs, by the way. Yes, exactly. Eventually that'll all happen. Yep. Okay, so here's what happens in evaporation. Molecules in the liquid are randomly going, different speeds. Some gain more energy than others because of the various collisions they happen. So one little molecule happens to be going this way, and it's hit by a really high, fast one, right? And then it's hit by another fast one, and it gets more and more speed, okay? And then it actually gets enough speed to break through and escape from this liquid, okay? The average kinetic energy of the remaining molecules in the liquid actually decreases, resulting in cool water. Okay, I have a question for you. Can you, I'm going to show you another little video. Can you boil water without raising the temperature?
Yes.
How might you do that?
You can do it in a vacuum.
Do it in a vacuum. Okay, so here's actually what I'm going to show you, which is kind of cool here.
The flash type evaporators that we used on ships before we used reverse osmosis operated on that.
No kidding.
Yep.
So the ships used to use flash, what do they call?
Flash type evaporators.
Oh, okay.
And,
very cool.
Destroyers had 2-stage, larger bird farm type ships had 5 stages, so they.
Oh, actually, no kidding. Let's see. That is pretty cool. YouTube, hang on, YouTube, watch.
But it's the same thing at altitude. You can boil water quicker, or not as quick.
You can boil, where you can boil water quicker. I'll show you another Hewitt one in a minute. Let's see, is this the one? No, it didn't go to it. Hang on.
Kung Fu Panda.
It's not what I want. Kung Fu Grandpa. I've not seen that one.
That was hilarious.
Is it pretty good?
Yeah.
All right, hold on. Water to ice, boiling, vacuum. Okay, hold on. Let's see. I think this is the one here. I hope this is the one. Yeah, that's the one. I typed it wrong.
We're going to demonstrate reduced pressure boiling by creating a vacuum in a glass vacuum jar and using an Edwards
A
pump.
vacuum jar.
By using and applying vacuum, we're making water change from liquid to vapor very
Watch
quickly and very effectively. Water at room temperature is placed into a beaker.
This is room temperature water.
Into a glass vacuum dome. We now open the vacuum isolation valve. You can soon see the vacuum gauge showing around 20 millibars of pressure. This is significant because it's the vapor pressure of water, and therefore the point at which it will boil at room temperature. At atmospheric pressure, water boils when heated to 100 degrees Celsius. That's because it's the point when water vapor pressure is equal to atmospheric pressure, and water begins to change phase from liquid to vapor. In this demonstration, we don't add any heat, but instead reduce the pressure. When this pressure is equal to the water vapor pressure, the water boils or changes phase, but at a much lower temperature. In fact, the energy for boiling is coming from the water, and consequently its temperature reduces. And as the pressure becomes lower, the water will eventually freeze.
Nice.
You'll see that even when removed from the vacuum chamber, the water remains frozen. A simple process, but one that's widely used in the pharmaceuticals and food packaging industries.
Yeah, so that was pretty cool. What was going on there was we were reducing the pressure over the water. Therefore, it made it much easier for those molecules on the top of the water to actually escape off the water. So you didn't need to raise the temperature. The only reason you raise the temperature, like in your house when you're trying to boil water, is because the air pressure is actually pushing down on the water and keeping those molecules of water in the actual container, right? When you remove the air pressure, those molecules go, oh, I'm free, and they don't have to go that fast. So that's why you don't need to increase the temperature. But what do we know about evaporation, which is why we sweat, by the way? What do we know about evaporation? What does it do to you? It actually cools you down. Okay, James says it cools you down. Well, why does it cool you down? Think about this. All of those particles that are coming off you, the ones that escape, were warmer than the ones that got left behind, right? So if something evaporates, if a water molecule evaporates, the ones that are left behind are actually, by definition, lower temperature. Okay? So evaporation is a cooling process. If you put alcohol, like the stuff you get at the chow hall for your hands, put that in your hands, it feels nice and cool. That's because because it's actually evaporating away. Okay, so that's what's going on with air. So evaporation is a cooling process. When the evaporation or boiling away of all that water was so vigorous, it just lowered the temperature of the ice, of the water, such that it would still boil off, but then it eventually got to that point where it just froze because it was too cold. And now it's about being in room temperature, or being in a room that's at room temperature, and it was cold enough to freeze. Isn't that kind of cool that it did that? It's pretty cool. And by the way, that's what freeze drying is all about. You take food, you take coffee if you want, do that to coffee, and it freeze dries, and then you put it in, you package it away. It's pretty cool.
Can you get iced coffee?
Not a bad idea, iced coffee. I hadn't thought of that. OK, let's see. And then this is what Tom mentioned earlier. Pigs, Tom says, don't have sweat glands. Turns out, don't know why. This is why they actually have to wallow in the mud. Whoop, can't see it yet. Come on, you can do it.
We're wrong all this time. They are just dirty.
They aren't just dirty. They're dirty because they go in the mud. And by the way, the mud actually does keep them cooler. So when they cover themselves with mud, they keep a little bit cooler. Okay, so that's what pigs are wallowing. Okay. You can also go from solid directly to a gas. Okay, dry ice does this. If you put dry ice and you have dry ice on a thing, it never goes into a liquid phase. It goes solid and then just what we call sublimes directly into a gas. Mothballs do the same thing. And frozen water generally too. I mean, if you just got frozen water on a pond, you never see that real liquid part of it. Okay? Same picture as before. Condensation is when you're going back into the liquid phase. Okay? And it actually warms up the liquid. Okay? Gas molecules are attracted to the liquid. They strike the surface and then slow down a little bit and get captured into the liquid, warming up the liquid. Okay? I like this little diagram. If you are in the shower, it's a little tough to do in Clueville, but if you're in the shower and you step out of the shower, you get cool, right? And let's say you turn it off, but there's still some water vapor in the shower. You turn off you step out, and it's like freezing cold. Step back into the shower, all of a sudden you warm up a little bit. Why is that the case? Because those particles of water are actually condensing onto your skin and warming you up a little bit. Okay? Evaporation cools you down. Condensation warms you up. Kind of cool. Kind of neat stuff. Okay? Anybody seen one of these little guys before? Yeah. This little toy drinking bird. This actually works by evaporation. Okay? On either side of its body, there's this. It's like water, but it's actually. I think what they do is they make this into a vacuum almost. Okay, so there's very little pressure up here. Okay, they take out. It might not be water. It might be some other kind of liquid, but I think it's water. And they make it very low pressure, so the water actually doesn't so you don't need to actually have much. You can actually get it so the water actually goes up to the top here. Okay. Yeah, it's actually liquid ether. It's not water. It evaporates at room temperature. So here's what happens. Okay, the temperature of the water on his little beak here evaporates away, okay, and vaporizes. That creates a pressure inside the, well, I guess it reduces the pressure, and the fluid starts going up the tube. Well, he's on little balancing things, so he flips over. Okay, he tips over, and then ends up his nose ends up back in the water here, but the fluid goes back down to the base. He flips back up, and now the same thing's happening. So you've got evaporation happens off the top of his head again, starting the whole process over again. And I know I have a video of this one too. Although I think you've all seen it before, but let me just show you what it looks like. Let's see, it's that. Oh, there we go. Hang on. I must have closed it. Google Djibouti. Have you seen that one before? Yeah. What's that? Yeah, that's right. I haven't seen I guess I have seen it once or twice. I think that's relatively new though. Let's see. Cornell physics. They do spell Google the same way. Here we go. All right. Right. Here we go. Videos by subject. We're going to go down to thermodynamics again, and then bobbing birds. Okay. So let's see. Let's just download a high resolution one, and then save it. Okay. Fast. Okay. Open it. Allow all those viruses. Sorry, J6. And there we go. So you can see the little guy's dipping down, and then he pops back up. And right now you've got evaporation happening on his nose here, okay? And that's causing a little bit of cooling, okay? And that cools down here, and then as it cools, it makes the air molecules in here actually are less likely, or aren't as high pressure. The cooling happens because it's not about pressure. I lied. As it cools down let's see, maybe it is about pressure. Thinking it's about, yeah, it is. It's about pressure. As it's cooling down, the pressure in here becomes a little less, and it can creep right up there. Okay. And then there you go, and then that one goes like that. So this will do this all day, as long as you have water in there. Right. Eventually the water in here goes away, but we'll just keep doing that all day. Okay. All right. Oh, all right. Okay. When a liquid changes phase to a gas, a liquid to a gas, does it absorb energy, emit energy, or neither, or become more conducting? What does it do? When a liquid changes to a gas, it absorbs energy, right? Because it's getting, think about it this way, the particles are getting more and more energetic. That energy's got to come from somewhere, okay? So the liquid, the part that's doing the phase change actually absorbs energy, okay? The rest of it might be cooling down, but the part that's doing the phase change is that, okay? And that's actually all I got for today. Oh, of course I didn't, did it just die again? Hang on, here we go. I don't like the fact that he's dying here. Kung Fu Grandpa. No, I tell you what, I'll let you go. Tomorrow, we will do some more labs. And I'll have something that's, I'll have a good one for, there we go. I'll have a couple good labs for you. If you could bring your computers, that would be great. The people who didn't get their homework done, come see me. And I will catch up with you guys tomorrow. Oh, you know, it is Easter tomorrow. I think we still have class. We'll still have class, but I'll let you go early. How's that sound?
Yeah, the Combat Cafe is closed tomorrow.
Combat Cafe is closed tomorrow, but you can eat before. Well, what time does chow start tomorrow?
18.
16:30. No idea.
16:30? So we got time. You got 16:30. How about,
Can you start class like a little bit later?
you want to start class a little later?
17:30?
We're getting some no's. 17:30, okay? I tell you what, we won't start till 17:30. Feel free to stop by, but we won't start till 17:30. I'll probably see you at Chow. I got to eat too. Okay.
Now, chapter 8 and 9.
For Monday, but I'll tell you, yeah, we'll talk about it tomorrow. Yeah. You might want to start reading though now. Okay.